Two, pick up from where I left off. Now, one thing I just did notice that I didn't talk about in binomial, so we're going to step back to the binomial one more time, is the mean and standard deviation. So for binomial, the mean is NP. I mean, we did talk about it because I talked about it in there, but the standard deviation is square root of NP 1 minus P. Of course, sometimes you'll see Q being what 1 minus P is. Just the probability of failure. Okay, moving on to geometric. So geometric, we saw last time I kind of went over Bernoulli real quick with Mr. Bernoulli was sipping his pee in his geometric cup until he realized it was piss, and his wife yelled stop. Her name was Binomial, by the way, and she said spit it out or you'll be on trial for drinking someone's pee. Okay, the significance, of course, is that sip, piss, PIS, and SPI, SPI, are all three the same conditions. And any geometric is Bernoulli, any binomial is Bernoulli. The distinguishing factor that makes a geometric is that you're stopping at the first success. You only have one success. The success can be defined as missing a shot or making a shot. It depends how you have it set up. But the whole point is whatever you're doing is probability, 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 and then times the opposite of the probability. So you have whatever you have, how many ever times, and then you're multiplying those, and it's the opposite of the probability at the very end. So that's the first success. And binomial, the distinguishing factor, of course, is that we talked about in the first video, is the trial is the set number. And you only have one trial. Or excuse me, not one trial. You have a set number, and it's make or miss. So it can look something like this, where the purple's the miss and the blue is the make, and it can be maybe in this order, but you're going to do 1, 2, 3, 4, 5, 6, 7, 8, 9 are here. So my n equals 9, and make or miss, and any order. All right, geometric. So for geometric, first of all, let's go over our formulas. The formula for geometric is going to be the probability. So probability for geometric is going to be the probability of failure, all these failures. So 1 minus P to the K minus 1, and then success, always to the 1. Okay, of course, this is geometric PDF where there's one success, and there's geometric CDF where there's many successes. In that case, you'll have from a lower bound to an upper bound. I'll talk about it in one moment. So let's look at and then the mean for geometric is equal to 1 over P. And the standard deviation, which we don't do very much, is equal to square root of Q over P. All right, so let's go ahead and look at a sample here. Let's say you have Ralph has a probability of 0.25 of making a shot. And I say, what's the probability that his first shot made is on the 6th try? So basically, I'm saying fail, 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 success. So the first step, what we're going to do is we are going to find out if this is geometric. So we're going to do our condition. So the condition, remember, Mr. Bernoulli was sipping his tea in his geometric cup until he realized it was piss, and his wife yelled stop, so stop at the first success. So probability the same, P is equal to 0.25, so this is what you would write on the test, is that probability equals 0.25, so probability the same each time. Independent, each shot is independent. And then success, failure, make or miss. And then stop after the 6th attempt. That's my success. That's the first success. Okay, so let's go ahead and write our formula here. Probability that x equals 6 is going to be my failure, 1 minus p, 1 minus 0.25, to the 6 minus 1 times the success of 25 to the 1. Guys, if you wanted to just write it out like this, 0.75 to the 5, 0.25 to the 1, that's completely fine. You don't have to have it in this. I'm just saying, this here, remember, is on the formula chart. And if you want to pull it directly off the formula chart, you can just do that. All right, so you can, honestly, I would just put this directly into the calculator. It's so much easier. But if you wanted to use the geometric PDF calculator, you are welcome to use the geometric PDF calculator, and that's in the same spot that the binomial and the everything else is. So it's menu, I'll just write it down just so you have it. Menu, probability, distribution, and then it's geometric PDF. And it's quite a bit further down, like because there's binomial and geometric is way down here. So about 5 or 6 further. So geometric PDF, the probability of success is 0.25 and the x value is 6. And so that's going to be 0.059 and that's it. So that's all the work you have to do there. So let's talk about a geometric CDF. All right, so a geometric CDF is if there's a range. So that would look like this. What's the probability of a shot made by the 6th attempt? So I'm asking for the success on the first time plus failure, success, plus failure, failure, success. So this is the first attempt, the second attempt, the third attempt, all the way to the one we just did, fail, 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 success. So that's what I'm looking for. I'm looking for to add up all the probabilities of succeeding by the 6th time. So the way I would do that is I would say x is less than 6 for this one, or you could put it as probability of 1x6, okay? And you would do the first one where you'd say, okay, I'm going to use this one just like we did, hold on here. This one is going to look just like we did up here where the 6, right? And so it would be the probability of 1 minus 0.25 to the 1 minus 1 times 0.25 to the 1. Plus dot, 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 plus. And again, you don't have to put 1 minus 0.25. You can put 0.75. But I'm just writing it out exactly how the formula is. So I'm just plugging numbers into the formula that is on your formula chart. So 1 minus 0.25 to the 6 minus 1 times 0.25 to the 1. Now, on this case, I definitely would use a geometric CDF calculator. The reason being is because obviously you try to add this up, it's a bunch of them. And so it just takes a lot more time than throwing in the calculator. On this one here, you can see it's just super simple to throw into the calculator. So I wouldn't necessarily need the calculator. So I'm going to go ahead and bring up my calculator. And the geometric CDF is, again, menu, distribution, or probability distributions. And it's right below the PDF. But it's the same thing. The probability of success is 25%. Lower bound's 1 and upper bound is 6 because I asked between 1 and 6 to be the first success, and that's about 82%. Okay, the end. If I ask you for your mean or ask you for your standard deviation, again, the standard deviation and the mean are on, the formula is on your formula chart. So you can just go ahead and use those. All right, so let's go back to the next topic. And the next topic is the normal model. Okay, so the normal model, let's look at normal. Okay, remember normal model. The only formula so far as we have for normal model, it will state that it's normal, or a binomial we already talked about, right? A binomial distribution has NP greater than 10 and NQ greater than 10. We studied this in the first video. When this occurs, it's normal. So we can use, we can use the normal, we call it approximation because it's close enough to use, but we use the normal. So it's gonna say there's a normal distribution. It's going to tell you there's a normal distribution at this point in your journey for stats. Or it's gonna be a binomial distribution where you're gonna do, I'm going to do spit, right? And NP and Q are gonna be greater than 10. And at this point, you are allowed to use either the binomial distribution or the normal distribution unless the directions tell you use this distribution, okay? Either one is fine if you use binomial. All right, so for normal distribution, remember, we have a nice symmetric data, and we have my mean, and we have my standard deviations. Remember, each one has about up to 3 standard deviations, and that's gonna be about 68%, 95%, and 99.7%. So this is 1, 2, and 3 standard deviations away from the mean. And remember, the two commands we use are normal CDF and inverse norm. The normal CDF command, which again is menu, stats, or probability, either way, doesn't matter. It gets you to your distribution menu, distribution, and the normal CDF. You have numbers, you have values, and it is asking you to find, thank you, the percentage. You're trying to find the probability. So for instance, it will tell you, Sally makes an average of 32 cookies with a standard deviation of 2.5 in each batch. Her results are distributed normally. So it definitely is going to tell you that, or it's going to be binomial with things that you can concur. Here's the different probabilities we're going to have. What is the probability her batch will make more than let's just say 35 cookies. Okay, so more than. So I'm looking, the first thing I'm going to do is draw a picture. And I know that I have a normal model with 32 cookies and 2.5 standard deviation. That's the first step. And I'm going to say, okay, this is 32. So that's 34.5, 37, and 39.5. This is 29.5, 27, and 24.5. So that's my normal model at 1, 2, and 3 standard deviations. And I ask specifically for 35 cookies. What's the probability of 35 cookies? So I'm right about here. So I know that's 35, and this is the probability I'm seeking. So I'm going to go ahead and write my probability statement. So my probability statement is, what's the probability that X is greater than 35? But that's the same as what's the probability that Z, remember my Z score is observed minus mean divided by standard deviation. So the Z is going to be greater than observed, which is 35, minus the mean divided by standard deviation. At this point, I leave that blank, and I'm going to go ahead and put it into my normal model and normal CDF. This is how I'm going to solve the normal CDF. If you're doing the Z-score table and you're comfortable doing Z-scores, then you continue and solve this for the work. Make sure you solve this problem, the 35 minus 32 divided by 2.5, to get what the Z-score is if you're not doing this particular one that if you're not using the calculator at this point. So I'm just saying here. All right, so for normal CDF, I go ahead and I'm going to do, for normal CDF, I need the mean is equal to 32. Standard deviation is equal to 2.5. The lower bound is equal to 35, and the upper bound is equal to infinity. You can put infinity or 9999. You have to put 9999 in your calculator unless you have a CAS, because it won't take infinity. So I'm going to go to my distribution menu. It's on the same one that binomial and geometric, all of those are. So normal CDF, lower bound is equal to, oops, sorry, I'm not typing in, I don't know what I'm thinking, sorry. Lower bound is equal to 35, upper bound 9999. This is a CAS, that's why you saw the infinity. The mean is equal to 32, and the standard deviation is equal to 2.5. So the probability is about 11.5%. So I'm going to go ahead and write that in there. So I'm just going to go ahead and write my sentence. About 11.5% of the time, on average, would Sally's batch have more than 35 cookies? And that's it. Okay, so that's for more than 35. I'm just going to review. I'm not going to go through the whole thing for the next part, but I'm just going to show you the setup. So if I ask for what's the probability that she has less than, let's just pick a number less than, let's say, 26. So that would be for less than 26. Of course, I'm just going to draw this out, 32. I've got my 27 here. So 26 would be here. And I would write my probability statement would be X less than 26. Z is going to be 26 minus 32 over 2.5. And you do normal CDF. And the changes, the mean and standard deviation would be the same here. The change would be the lower bound would be negative 9999, and the upper bound would be 26. Okay, and then you would come up with everything else the same. Okay, what if I said has between 28 and 33 cookies? So that looks like this, 32, so 33 is here, 29.5 is here, so 28 is here. So this one's going to look like this, 28 less than or equal to X less than or equal to 33, which would be the probability that 28 minus 32 over 2.5. So you're just going to basically do it for both of them. You're going to turn them both into z-scores. And then you're going to just put that blank there. And same normal CDF. The only thing that changes is your lower bound at 28 and your upper bound at 32. Everything else stays the same. Okay, what if I ask you if it says the top 20%? So now I have this value, 32, and now I have this, 20%, and I have this y value that I don't know. So this is going to be, what's the probability that y, because I don't know the y, is greater than x, because this is what I'm looking for. And so this is just going to be, let's turn into it a z-score. Z is going to be greater than y, because that's my unknown. My unknown value now is going to be y minus 32 over 2.5. And we do know the percentage at 0.2, because what I'm trying to find is this y. If you're doing it by hand, of course, you would find the z-score of 20%, and you would do it by hand. But if you're doing it in the calculator, we're going to go inverse norm, because the inverse norm calculator has a percentage. I know the percentage, and I want to find the value. So I said area. The area always is the area from the left. So the area is going to be this area here. So So I know that top area is 20%, so the bottom area is 80%. So in the calculator, when it asks for area, it always starts in the left. So you'll put in 0.8. And the mean and the standard deviation are the same that we've been doing, 32 and 2.5. So let's go ahead and do that. So use same distribution menu, inverse normal. The area here is going to be 0.8. The mean is going to be 32, and the standard deviation is 2.5. And you get 34.1. So this here is 34.1. So about 34.1 cookies on average are and above or in the top 20% or something like that. All right, so if I said, I'm just gonna go over, remember, bottom 10%, let's do bottom 10%, same thing, except you're gonna be 32, it's gonna be now 10% here. Now the only thing that's gonna change, I mean, everything else is the same, the probability that my y is less than x, and that's gonna be the probability that z is less than y minus 32 over 2.5. Just wanna check something, yeah, okay. All right, and then now, because I'm looking for all of the y's that are this way. So, and that's equal to 10%, 0.1. Okay, so when I do my inverse norm, remember, I'm looking for an area that's starting from the left. Well, that's already at the left, so it is 10%. So it's the area that's given. Okay, the mean and the standard deviation are going to be 32, of course, and 2.5 in the same way. Okay, here's a little bit tricky one. What about if I ask you for the middle 40%? So the middle 40% is going to be this. 40%. But remember, this is symmetric. So therefore, this half is going to be 20%. And this half is going to be 20%. Which, if this here, smack dab in the middle, is 50%, let's do some math and say, okay, 50% minus 20% means this here, left, is going to be 30%. So when we do our inverse norm, the area for this one here, because that's the value I'm looking for, y, is going to be 0.3. And this one here, the value, let's say I'm looking for is, let's just say g, is going to be this 30% plus 20% plus another 20%. So it's going to be 70%. So that one, if I did inverse norm, is going to look for 70%. And with the mean and standard deviation, everything else the same. Okay, let's jump to z-scores. Just since we're here, reminding me of z-scores is observed minus mean divided by standard deviation. And we're going to actually solve the same problem except with z-scores. So we're going to jump back way here to the very beginning that Sally had 35 cookies with a mean of 32 and standard deviation of 2.5. So I'm going to just draw this out just to review kind of where we were. Remember, I had a normal model, 32 and 2.5, and I had this as 32, 34.5, 37 and 39.5, and I had this here as 29.5, 27, and 24.5. And I ask, what's the probability that, I'll just go from here. So what's the probability that a z-score is, I'm going to say, greater than 2.2 in this particular instance. So, or if I say, what's the value? Let me do it that way, because that's, what's the value with a z-score of 2.2? Okay, so the first thing I want to do is I want to go ahead and convert this to a z-score. All right, when we convert it to the z-score, let's convert each of them to the z-scores. Obviously, z-score is going to be observed minus mean divided by standard deviation. So if I convert this one to a z-score, it's going to be 32 minus 32 divided by 2.5. Oh, obviously that's 0. This one's going to be 34.5 minus 32 over 2.5. That's 2.5 over 2.5. Obviously that's 1. You see the pattern. Basically, this here, this is why the z-scores become 0, 1, 2, 3. And so what this is this now is a normal model with 0 and 1, and it's completely unitless. But we're going to solve the same thing. I'm going to say, all right, we're going to take this z-score, so let's do this one right here. Or wait, sorry, let's do the one we already solved to save some time. So the one we already solved was 35, yes. 35, and we found it 11.5%. Okay. So if I said 35, which was right here, we found from the above problem that was 11.5%. Okay, so we're going to do it now on the z-score table. So let's find what the z-score is for 35. So observe 35 minus 34.5, oops, divided by, minus 32, because observed minus mean divided by standard deviation. So we get 3 divided by 2.5. And when we do it in the calculator, we have 3 divided by 2.5, we get 1.2. So this here, you notice, is going to be the same proportion shaded. So if I were to do this one now in the calculator of the normal CDF, lower bound 1.2, upper bound infinity, mean of 0 and standard deviation of 1, let's see what we would get. Lower bound 1.2, upper bound infinity, mean and standard deviation of 1, 0 and 1. It always has the z-scores already in calculator. We get the same thing, 11.5%. So you can see that the z-scores go back and forth to the values. And yeah, that's all you have there. I'm going to give you one more challenge one. Let's pretend that it gives you the same problem. Oh, wait, nope. Not same problem. This time it tells you this. Let's go back to here. Let's say it gives you this. Let's say this is 50 and this tells you this is 15%, and this says this is 20, and this tells you it is 5%. All right, and ask you with this, and it says it's normal, and it says what's the mean and what's the standard deviation of this. Go ahead and try to solve it. All right, so the way you're going to do this is with z-scores, because you don't have a mean, you don't have a standard deviation. So therefore, without those two pieces of knowledge, you cannot use the calculator. So what I'm going to do is I'm going to use that I have two separate values. So I'm going to find, I know that I have for the z-score for 5%, which, by the way, we can look up in the calculator or the chart. So let's go ahead and find that. So the z-score for 5%, the way you would do the z-score is you're like, okay, remember up here where I was saying for it would be like this. I'm at 5%. And that would mean that I am looking for an inverse norm. Because I know with my z-scores, I always have a mean and a standard deviation of 0 and 1. So I'm going to do an inverse norm, so I'm going to do an area of 0.05. So I'm going to be able to find the z-score for 5%. Because remember, with the z-score, I told you with the z-score chart, the mean and standard deviation is always 0 and 1. So we're going to use that to our advantage and jump back here to my inverse norm. And we're going to find the z-score to be 0.05, 0 and 1. And so that's negative 1.645. Let's go with negative 1.645. Okay, how are we going to use that? Well, z-score, remember, is a z-score is observed minus mean divided by standard deviation. Okay, so this z-score, that's my observed value for that z-score. So I'm going to say this is my observed is 20. I don't know the mean, and I don't know the standard deviation. But that's equation 1. And what I'm going to do is I'm going to do 2 equations and 2 unknowns. All right, in equation 2, I'm going to do the z-score for 15%. So we're going to do the same thing, but but instead of 15% for the area, remember that my area always starts from the left, so I need this shaded yellow area. So I'm going to use, of course, for inverse norm, my area, I'm going to use 85%. Same mean and standard deviation are always 0 and 1 to find my z-score. So z-score for 15%, we're going to do the same thing. And so I have lower bound, or sorry. Oh, I don't know what I'm doing. I'm sorry, I'm on the wrong thing. Inverse norm. I need to go to inverse norm. There we go. My z-score for 85%, 0 and 1, is going to be 1.036. 1.036 about. Obviously, if you round differently, you're going to get something a little bit different. So my observed value is 50 minus mean divided by standard deviation. Now, guys, you see I have two equations, two unknowns. So now you could do substitution method. You could do all kinds of methods. I'm going to show you the method that I'm going to use. I'm going to use our calculator where it has nsolve for two equations, which is called linsolve. So I'm going to be using linsolve, but linsolve is linear, and so it will not allow you to have a variable in the denominator. So we're going to have to just multiply this to negative 1.645s equals 20 minus m. I'm going to call this one x and this one y. So in my calculator, I'm going to put 1.645 x equals 20 minus y. Same thing here. 1.036s equals 50 minus m. So 1.036x equals 50 minus x, or y, sorry. So here are the two equations going into my calculator. So 1.645, and then negative 1.645 and positive 1.036. So let's go here. So for your calculator, you're going to go to menu, algebra, and you should see, yours is going to be a little different. Mine's systems of equations. So it depends if you have a CAS or not, but it's linsolve. And so I'm doing linear equations and two equations, x and y. You could change that to m and s if you want, but I just did this. And so I have, remember, negative 1.645, and my equation says x. So, sorry, I missed. X equals, and it is 20 minus y. So 20 minus y. And then for the next one, I'm wondering if it's going to be yelling at me because it's a capital Y. It might. So let me just make sure it's not. There we go. Oops. Okay. And the next one is going to be 1.306. 306 or 036? 036, yes, I thought. 036x equals, okay, is going 50 minus y. There we go. All right, hit enter, and my answer is 11.18 for x and 38.4 for y. So remember, my x was my standard deviation, so my mean is going to be about 38.4, and my standard deviation cookies, make sure we label, and my standard deviation was, I think, 11.2 cookies. All right, and so that's how you would solve that one. All right, let's go to random variables. Random variables, remembering how to add random variables, multiply random variables, et cetera, here's how we're going to do it. So random variables, remember mean and standard deviation. For mean, x plus y is going to be the mean of x plus the mean of y. Standard deviation of x plus y, you cannot add the standard deviations. You can add the variances, so it's square root of standard deviation of x squared plus standard deviation of y squared. Same with subtraction. If I were to make these a subtraction problem, this would be subtracted. If I made this a subtraction, this would still be an addition problem. Because you cannot have, number one, what happens to your spread is it still spreads out. And actually, I'll just go ahead and show you why that is. So let's try. Let's just come up with a really small data set. Let's just go 1, 2, 3. Let's make it nice and small. And then y, let's do this. Let's do 4, 5, 6. Okay. Well, we obviously know the mean of x is equal to 2 and the mean of y is equal to 5. When we add these together, when you add them together, we're going to have x plus y, and we're going to have, this is how you add them. You do this one plus this one, and this one. So, and then so forth and so on. So now you're going to have the mean here. We're going to have x plus y is going to be 1. Oh, sorry. You're going to have 5, 6, 7. And then we're also, of course, this is still 6. And then we have a 7 and we have an 8. And then this one here, we have a 7, 8, and a 9. So that's my new data set with the mean, obviously, smack dab in the middle. The mean of x plus y is smack dab in the middle is still 7. Okay, the standard deviation, if we go into here, let's go ahead and make this into a standard deviation. And then let's subtract it also. And then we'll do all of that, all the other stuff. So x minus y, we're going to do the same idea, except we're going to start with my largest one and subtract and go from there. So 6 minus 3 is going to be, 6 minus 3 is 3. 6 minus 2 is 4. 6 minus 1 is 5. And then 5 minus 3 is 2. I need to move these over. These are my largest ones, sorry. 5 minus 2 is 3. And then 5 minus 1 is 4, so that's already done. And then 4 minus 3 is 1. So here is my x minus y. But I do want you to notice now we're going to be, so for mean x minus y, you can see obviously it's smack dab in the middle of 3, which 5 minus 2 is equal to 3. So that works out nicely. Now, standard deviation. Let's look at standard deviation. Okay, I want you to see and notice how far apart 5 and 9 are. 5 and 9 are 4 apart. 1 and 5 are 4 apart, and each one in between are 1. So these here are going to have the standard deviations of x plus y is going to equal the standard deviation of x minus y, because every single value is 1 apart, and this range is the same. So you can see the standard deviations are going to be the same. The spread's going to be the same. So that helps hopefully show you why the standard deviations are the same. All right, let me just kind of show you the difference of standard deviation with you multiplying standard deviation versus adding. So let's talk about movie tickets. Let's say that a movie ticket costs about a mean of $10 with a standard deviation of $2. And you're nice and you want to take your friends to the movie, so you buy 4 tickets. Okay, so what's the average price that you would buy if you went to lots and lots and lots of different movies, and every time you bought 4 tickets and you were the one that was your thing, you took your friends to the movies every week, and then after a year we find the average of what it was and we found the mean standard deviation of this. So the average, if you bought 4 tickets, you bought 4 separate tickets. So you did literally this. You did x plus x plus x plus x. You did 10 plus 10 plus 10 plus 10 to get an average of $40. For standard deviation, what did you do? For standard deviation, x plus x plus x plus x. And so remember, you cannot add standard deviations. You have to add the variances. So we're going to do this. 2 squared plus 2 squared plus 2 squared plus 2 squared. You obviously know that equals 4 times 2 squared. So if we just do a little bit of math, that's going to be 4 times 4, and that's obviously going to be $4. Let's compare this now to what happens if I'm going to go to California, and everything in California is very expensive. And because it's so expensive, sorry, friends, I only can buy 1 ticket because everything's so expensive. And the reason I only can buy 1 ticket is because the cost is 4 times the cost as it was in Texas. So now I'm buying one ticket. I'm still going to the movies every week, but I'm only buying one ticket. And that ticket cost 4 times as much. So now the mean of my is 4 times X, which is going to be 4 times $10, which is $40. The standard deviation is the part that we have to be careful about. The standard deviation is going to be I'm multiplying this. So essentially what I'm doing, I'm saying, okay, I'm now saying the standard deviation was $2, but now the new standard deviation is going to now be 4 times 2, which is $8. And this is now my new standard deviation because instead of me adding 4 separate, essentially what I have done is I have multiplied my standard deviation by 4, not added them separate. So you can see, obviously, the means are the same if I add it 4 times or multiply times 4, but the standard deviations are very different, where this $4 is a representation of 4 separate tickets, and this $8 is a representation of taking one ticket and increasing the price by a factor of 4. All right, I believe that should be, let me see if there's anything else on my list. At least one, yes. I want to talk to you, remind you about at least one. Whenever you have something that says at least one, if I have the probability of at least one, that's equal to probability of, that's equal to 1 minus the probability of none. Let's look at this here. If a probability of choosing a certain color, let's say choosing red, is equal to 0.3. And I have red, 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 and I have green, green, and I have blue, 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 and then I have yellow. I think that's 10. Yes. All right, and I say, all right, I'm going to grab one of these reds and I'm going to put it back, but I want to know what's the probability of getting at least one red out of 4 pulls. So I'm grabbing one and putting it back, grabbing one and putting it back, grabbing one, putting it back, and I want at least one red. Well, if at least one red represents, let's go ahead and draw out. I've got 1, 2, 3, 4 pulls. What that represents is I could get a red here and the other color's there. I could get a red here and the other color's there, a red here or a red here. Or I could get reds here and no reds there. I could get a red here. Sorry, that line was, and a red here and the other, and so forth and so on. The list goes on. And so the problem is each of these probabilities have their own individual probability. So this one would be red would be 30% times 70% times 70% times 70%. Oh, this is also 70%, 30%, 30%, 70%. This one's 30%, 30%, 70%, 70%. Anyway, the list goes on and it becomes very, very complicated. So on the other side of this here, this big, all these combinations, all the possibility that there's at least one red in my pull. But there's another circle that's a lot simpler where there's no reds in my pull. So they could be basically, this is what they are. No red, no red, no red, no red. Oh. There's only one possibility of no red, no red, no red, no red, and that's 70% times 70% times 70% times 70%. That's so much easier. But all of the no reds possibility plus all of the ones that have at least one red are my total possibility of 1. So that's why 1 minus the possibility of no reds equals the possibility of at least one red. So it's a lot easier to do it on this case. So on this one, what's the probability of no red? So this is going to be 1 minus the probability of no red, which is 0.7 to the 4. And that makes it a lot easier for you to do that. All right. I do want to show you one in a geometric sense because a geometric is weird. So let's do a geometric probability of at least one. So what's the probability if let's give the backup first. So let's just shooting basketballs again. Shoot a basketball. Probability of, let's say, 80% to make it. What's the probability that at least one make will happen after the 8th shot. So here, what I'm saying is let's say before. Sorry, I'm just trying to think what's before the 8th shot. No, after. Sorry, I'm going back and forth. I'm just trying to think of the one that's a difficult idea. So what's happening after 8th shot? Yes, this is correct. Sorry. So what I'm saying is 1, 2, 3, 4, 5, 6, 7 are not. So we know that these first 7 are 0.2 to the 7th. We know that. But what we don't know is what any of these others are. So I'm essentially looking for this one. I'm looking for this, right? Plus I'm looking for this one, 2 to the 8th times 0.8. Plus it happening 9 times, like I'm ready for 8 times and then check, and then 9 times and then check. I'm looking for all of these. But in theory, this could go on forever. So this is a lot easier if we say what's 1 minus the probability of it not, instead of it at least 1 after the 8th shot, if it happening, 1 minus the probability of it happening by the 8th shot. So happening by the 8th shot. So this is saying after the 8th shot. So essentially, I guess after should have really been, I apologize, it should have been 1 more, right? 8 no's. And then the 9th shot happened. So it really should have been that. So I'm saying because this keeps going forever and ever, it's going to be a lot easier to say, let's do 1 minus the probability of happening by the 8th shot, which is 0.28 to the 7th times 0.8. And we're going to subtract this probability up, not just the 8th, because then I have to say, what is this? Plus 0.27, or to the 6th times 0.8, plus so this would happen on the 7th shot. I got to do the 6th shot. The 6th shot is this. That's the 6th shot, and so forth all the way to the 1st shot. But that's going to be 1 minus, is going to be an easy geometric CDF, and you'll have your lower bound at 1, your upper bound at 8, and your probability at 0.8, and that's going to get you your answer. Of course, if you were doing this out, 1 minus, it's going to say, okay, from 0.8 to the, or the probability of not making, which is 0.2 to the 1 minus 1 times 0.1 minus 0.2 to the 1 plus ... plus 0.2 to the 7th and 0.8 to the 1. What this represents is this happening on the 1st shot, the 2nd shot, the 3rd, the 4th, the 5th, the 6th, the 7th, and this is the 8th shot. So this is the probability of it happening by the 8th shot. So the opposite, 1 minus, is the probability of it happening after the 8th shot. All right, that's the end of this video, and I'm going to go ahead and in the next one show you some problems.